Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Dear students, today we have theorem. Let G be an abelian group and let H be the set of all those elements of G whose order are the powers of a fixed prime P. Then show that H is fully invariant subgroup of G. Proof. Let G be an abelian group. As G is a abelian group, it means that all the element of G must obey the commutative property. And for a fixed prime number P, let H be the set of all those elements of G whose orders are the power of P. It means that H contains all those elements in which their order are a power of P. We show that H is fully invariant. For this, we first show that H is a subgroup of G. Clearly, E belongs to G is the identity element, and this identity element belongs to the group G is such that the order of E is equal to 1, and we can write 1 as a power of P, that is 1 is equal to P power 0. It means that E belongs to H because E is an element whose order is a power of P. So that it means that H is non-empty. That is, H contains at least identity element. Now let we take two elements x, y belong to H. Then the order of x and y are the power of P. This implies that the order of x and y inverse are the power of P, because we know that the order of y is equal to order of y inverse. If the order of y is equal to P, then the order of y inverse is also power of P. This implies that the order of x, y inverse is a power of P. If the order of x is a power of P and the order of y inverse is also a power of P, then x dot y inverse is also an element whose order is a power of P. If x, y inverse whose order is a power of P, so this implies that x, y inverse belong to H, because by the definition of H, because H contains all those elements whose order is a power of P. This implies that H is a subgroup of G. Now we show that H is fully invariant in G. For this, let alpha be any endomorphism of G, and we will show that H under alpha is a subset of H. Let we take an element y belong to H alpha. So by definition of H alpha, there exists some x belong to H such that x under alpha is equal to y. If x belong to H, this implies that the order of x is a power of P. And we also know that the order of x alpha is a power of P, as we know that the order of x is equal to order of x alpha. Under any homomorphism, the order of x is equal to order of x alpha. We have previous result. If order of x alpha is a power of P, it means that x under alpha belongs to H by definition of H. This implies that y belongs to H. So we have taken an element y belong to H under alpha. So y also belong to H. So y also belong to H, and hence H under alpha is a subset of H. This shows that H is fully invariant in G. Now we have a next theorem. Prove that the subgroup generated by all the elements of a finite order in a group is fully invariant. Let G be a group and H be the subgroup which is generated by all elements of the finite order. We show that H is fully invariant in G. For this, let we take an alpha from G to G be an any automorphism, and now let we take an element y belong to H under alpha. So by the definition of H under alpha, there exists some x belong to H such that y is equal to x under alpha. Now x belong to H. This implies that x has a finite order by the definition of H, because we know that H contains all those elements which has finite order. So x under alpha has a finite order because we know that the order of x is equal to order of x alpha. So y has a finite order because y is equal to x under alpha. If x under alpha have a finite order, then y also have a finite order. So by definition of H, this implies that y belong to H. Thus we have shown that if y belong to H under alpha, then y belong to H. Hence, we have proved that under alpha is a subset of H, showing that H is fully invariant subgroup of G.